Okay, first about the hub that RMIT is part on. The hub, it has a number of Australian universities and 2 international universities from the US and UK. So it's led by the University of Swinburne, and currently it has 11 companies, but we're growing, we're still growing. So we have Mona's joining in 2 more companies very soon. So in terms of industry participation, we have strong industry participation, and you know, I want to tell you a bit about the objectives of the hub. Yes, so it's a very narrow aim. The hub has very narrow aims. It's not about improving, you know, the world. It's about improving manufacturing in really 4 areas, which is productivity, production, increasing productivity, increasing efficiency, increasing product quality and consistency, reducing unplanned maintenance, and reducing energy use. That's it. So all of these partners, they work on this, towards these aims. This helps also articulate the value to the industry partners, what they will get out of this research. Right? And how we're going to do that? This involves a number of technologies, right? And so we have 4 programs. And the first program is about is digital twins for manufacturing. It's a buzzword. Digital twins is a buzzword. But what it means, one thing that is not made clear in the trade press or papers, is manufacturing as well as other areas like the built environment, defense, and so on. They have a lot of physical assets. So they have complex manufacturing machines, you have materials and people, and you have people also contributing to the production, right? So if you're talking about creating AI and computer science solutions, you have to represent this in the digital world, in the cyber world. And also you have to communicate between the physical and cyber world. That's the main difference. So somehow, and of course there is IoT in this space, right? But IoT, it does this, but it does it for very simple sensors. Things that have very simple representation, they provide data, that's it. Now, when we talk about complex materials, they have autonomy, they have some autonomy, they have the same as with people, and so on, right? So that's really the purpose of this program, is to do that. And then, of course, the physical AI, I call it physical AI here, in machine learning, it's about using the information from the digital twins to optimize this, the goals of the hub, right? Increase productivity, increase the resilience in manufacturing production. And of course, we want to put all of these aspects in a platform, because a platform reduces the cost and makes application development easier. So we create an open source platform to give to users of the projects and also give to the industry. So that's the third block. And of course, all of this cannot happen unless you work with very closely with the industry partners, because we don't know a lot about the machines. We don't know, we know part of what we need to know. So the industry folks know the other part. So we need to help them in the projects to work with us. And that's really, the co-creation is how to do that and how to train them in the stuff we do. Okay? And so let me go a bit deeper here. For digital twins, I want to point you to this report that was published at the end of last year by the Academies of Science, Engineering, and Health, 3 different US academies. They published a report for this. My advice is go look at this report. It's quite an interesting report because it's not technical, but it outlines the principles of what is a digital twin, right? Because, for example, the report says the digital twin is a representation of a physical entity, but it has to be updated continuously. It's not a model, it's not a simulator from the physical world. It has to get data continuously from the physical world. And it represents an individual, not a class of, it's not a machine of type A, but are individual machines in different production, like maybe the same type, but they're individual digital twins. Interesting enough, the biggest supporter for this is the Academy of Health, because they think this technology is critical for personalized health. And I can give you a lot of examples. I don't have the time, but health provides a lot of interesting examples. So what we do here, we want to do this for manufacturing. And we have an opportunity to actually pioneer this area, because all the US at this point is focused on regenerative models and stuff. So there's very little work done in universities and research centers about this area. Okay, so go a bit deeper, okay? So that's a kind of agreement in the literature, how you can see a digital twin. It has a physical layer, it has a virtual layer, it has a what's called digital threads, a way that the physical communicates to the digital, okay? And so a physical thing, I want to introduce the fact that the physical thing is not just the physical entity, it's not just the machine, it's not just the person or just the material. It's actually the machines and sensors that helps you get the data and communicate with it. Okay? I can give some examples, similar examples. So this here is a device you attach in milk tank, and this device measures temperature, cooling rate, volume, content in fat, and protein of the milk. So this particular device is part of the digital twin, and we've made it so we can attach it to a standalone existing. Okay, so this is part of it. This one is from composite curing. This is from a project with Boeing that I'll talk a bit more. And the sensors, you measure viscosity, temperature, flow of resin, and pressure in the mold are part of the physical twin. Here is sensors, wearable sensors for humans that we can. So going back now, so the virtual twin. Well, you have to represent things, okay? When we say represent, for example, in a recent project we're doing with the steel industry, it took us 6 months to understand the parameters we're getting from the machines. And this took 2 engineers from that company working with us every week, on different problems and spending 4 hours every week in meetings just to understand what's going on with this. What they mean, all of these things mean, right? So, well, there is a technology you can help with that. For example, there's some knowledge-based technologies like semantic graphs, okay? Concept graphs can be used to represent this. It's very appropriate, not only represent this, but, so instead of having to spend 6 months with engineers, you do it once, and after that you have access to this information. Anybody can read it, right? And also you have to represent some other attributes that we're going to talk later on, which are the physical relationships and dependencies. Because we're talking about physical entities, and this has to be represented. And of course, digital twins contain AI, right? Because the optimizations that happen through AI, at least in this concept of digital twins. Now, another thing that it's critical is the digital threads. This technology, it already exists. Actually, this is the main contribution of IT platforms. There are thousands of IT platforms in the market today, And one concept they have is that you talk to the physical sensors in this case, using protocols, any protocol, industrial protocols, or normal IT protocols, okay? And so we adopted, this is actually the biggest innovation in IoT in terms of going from the information bus we have in digital systems to protocol-based communication. This is fundamental shift because hardware talks protocols, doesn't talk information bus. Okay, so that's okay. So if we try to put in, so just to give an idea of what are the elements of this, I'll go a bit deeper and I'll go to the AI after that. So the elements are, so this is the virtual twin, the physical twin, the protocols and so on. Okay, let's talk about the description. Okay, I talked about concept graphs, right? And the concept graphs, there is some existing technology for that. For example, there is a standard we developed years ago with an international consortium led by CSIRO. And this is, there's two standards. One is the W3C semantic sensor networks and SOSA, which is also an OGC and W3C standard. And this tells you how to describe sensors and their data. So this can be used as the lowest element when you want to describe a machine, or you want to describe a product, or you want to describe a person. Remember, all of this, they have sensors in the physical twin, either add-on sensors or incorporated, built-in sensors. And so you can start representing this on the bottom layer using this technology, right? And it's already exists technology is a standard, or any other standard like that, okay? I'm not going to get to details of this, because we don't have a lot of time. So a digital twin has inputs and outputs, and now what's interesting here, unlike other things, the inputs in digital twin are two things, right? They're the normal data inputs, like for example, measuring temperature in a composite product is a normal input that comes from a sensor, but there's also machine settings. So what is the impact of machine settings? Well, the impact of machine settings is that they change what the machine is doing. So the data you're getting is different. If you change the setting, it's a dependency. Okay, so this is one interdependency, if you like, in the data. You have to deal explicitly with. And I will give you an example of that later on. Okay, also you have to take into account that there is some automation on the machine. So the machine has its own control room, or it's a human that can act differently. So this solution has to be collaborative. It cannot be controlled, like the manufacturer has talked about control. There's no control here, absolute control, but it's actually a collaborative situation. And finally, in the manufacturing area, you have to have translation, because the data you get from the sensors is not the data you need in the application. Let me get into that a bit more. And for that, for the translation, you need to have AI. So the first type of AI in the digital twins is translation AI. Let me give you some examples. You're familiar with using cameras, right? Well, camera data is translated from pixels to information on the application data. It's translation, right? Here are some other examples from existing projects. In this situation here, you have a welding machine and the cameras that look at the weldings and assess the quality of the welding. Is the welding fit for purpose, right? The quality and consistency. Well, this has to be assessed again by AI, because the application is to, is the product ready to be released or it needs rework? So the camera gets the images, okay? But there is AI there that is not translating the data, the raw data, to spatial information, but normally, but translated to quality assessment for a particular welding. Same here with composite airframe. For example, in this case, the data is temperature, viscosity, and so on, right? But what you care in the application, for example, if you look at the composite viscosity, viscosity sensors, they produce signals, electrical signals. So you have to take that and produce measurements in viscosity, right? And again, and I can tell you off the loop how you train these models, right? And here is another one. This is from the device I showed you before. And the sensor there, it's actually a spectrometer. So you take spectral data and you have to convert that to protein and fat measurements. And we have a paper in IEEE transactions of industrial informatics about this. Okay, you can, so it's quite interesting. One of these are part of it, right? You understand you need to have translation. There is AI that does that. That's not, each of these digital twins may have multiple of these translation models. It doesn't need to be one, right? And now, in terms of the optimizations we've talked about the improvement in efficiency, the improvement in product quality, there's a different AI that takes the translation data, right? What the other AI produces. So it's a pipeline. Okay, so let me give you, first of all, very quickly go through the challenges here. 5 minutes. Yeah. All right, so the problem with manufacturing, there is not enough data. Okay, the same problem is in robotics. If you put a robot in a new area, there is not enough data. How are you going to create this data? Okay, and also the data, there are a lot of changes that happen through the settings and so on. As a result, when you create a model, you take the data and try to train a model. And we have done this hundreds of times, okay? The accuracy of that model is around 50%. Because there's not enough data, and the data contains a lot of physical and dependencies type of setting outputs, right? So, let me give you an example. Let's say you have an oven. You turn the oven, put the oven to 100 degrees setting, 100 degrees. When do you think the oven is going to go to 100 degrees? Does it go immediately? No. So if you're using the data from the time it takes the oven to warm to 100 degrees to train your model, you're injecting inconsistency. Then, let's say you move the oven to 100 degrees. We're going to get different data. If you don't know which are the settings and what settings were, the data you produce creates inconsistency. That's the reason you're getting 50-degree inconsistency in a lot of these manufacturing data sets. We have trained a lot of different models, the same result. Okay. Now, so again, the optimizations are about improving efficiency, product quality, and all of these things I talked before. And the problem, as I said, is the model accuracy. Okay? And another new element is you want to go to a closed loop setting. I don't know if you know what a closed loop setting is. So there is one approach: you collect the data, you analyze it, build a model, and use it. And you use it next time. closed loop means that you predict the outcome and you make the changes in real time to produce the thing you should produce without needing it. It's another challenge that you have to use. Okay, I'll give you two examples and we'll close down. The first example comes from, this is a port manufacturer, it's Becca, that makes Vegemite, very famous Australian product. And so I'm going to talk about the digital twin for this. Okay? This is the dryer. The dryer is a building and is the bigger consumer of gas in the state of Victoria. Good example? Okay, so the problem they have is the plant productivity is low, it's below, efficiency is below 50%, according to the data collected for a year. They think it's 60%, but it's 50%. And there is a lot of variation to the raw material. And there are engineers there that make changes in the production settings during the production to cope with it. Okay, so how we can create a digital twin that increases the production efficiency for above 50%, significantly above 50%. Okay, how do we do this? Of course, this so the consistency that we need to achieve is 63% solids, right? And to do that, because the product varies, the raw material varies, you need to determine the appropriate settings for the evaporator. So the AI, what it does, it recommends settings for the evaporator or applies the settings directly to the machine through the PLC. So this is the physical twin. This is the machine, and here is the sensors and actuators. So I'm not going to go through them. Okay, this is where we get the data, and this is the representation of it. These are the dependencies, and there's also a physical dependency. When we change settings, the machine takes 5 minutes to adapt to the settings. So if you keep changing settings without waiting for 5 minutes, you don't know what you're getting. Okay, so we build a model for that and so on, and predictive model, and we build both in a recommender system and also a program to apply this directly to the machine. And what this does, you can see here, you can see here the most critical readings from the sensors, and here you can see what's the current setting for various settings, what's the implemented setting, and that's a what-if scenario. You put something there and see what the AI will tell you through the setting. Okay, so that's what. So that particular thing collected data for a year. So that particular thing improved the productivity here by 17% the first pass. That is the twin and the AI for it, and 100% the second pass for this one. Similar problem exists in composite manufacturing. There's a project involved here in Melbourne. The objective of this project is to improve, to reduce the time for composite curing. Because composite curing takes several hours to bake the composite in the oven and then leave it overnight. So if you can shrink the time, you increase the productivity of the factory. This factory cannot keep up with orders yet. Right? And again, that's the stages of, we're talking about the resin injection and the composite curing stages. So that's the sensors here, that the physical twin. I'm going to cut this short, so this produces a curing prediction using the sensor data. So it's a predictive AI model that predicts the curing speed, and it does this during curing, right? And And how do you know now? The question is, how do you know that you have a good product, right? Because you can spit things out, but the product may be bad. Here is how you know. So this is the curing curve of the manufacturing for the resin. And here is what this AI ensures. That the curing curve stays very close to the optimal curing rate for this product. So that's how you know you reduce the time, but also the resin is good. Okay, and the last, this is about humans. Let me do this doing for a human. Okay, so through that, I'm not going to show you this video because we're running out of time, but we can estimate the productivity of each worker. Okay? Because we measure the product and we measure how they do the work, what they're doing, they're producing, they're not. Yeah? And you can see here, one of the interesting findings here is that the experienced workers work only 63% of the time, but produce 1/3 more product. Quite interesting. Anyway, so I'm not going to go through other things. I'm just going to conclude here. So I went through digital twins and I went through physical AI involved in manufacturing. I didn't talk a bit about the platform itself. There is, I have a PhD student finishing right now in this area. And co-creation is a different talk. So, so what is remaining here? What are the remaining challenges? The remaining challenges are really the expertise of the industry to take these solutions. You know, they need to have people who understand AI, understand how to deploy these solutions, right? One. And the second is the cost of AI, because AI is very costly for this environment. I'll give you an example. We had 3 projects with Asahi. Asahi, just in Melbourne, makes 250 products. For every product, you need a different model. For every production line, you have to multiply that with the number of products. You know, if one of the settings, if one machine is replaced, you need a different one. Who's going to build these models and who's going to pay for it? So perhaps the solution is we have AI that builds AI. So this is what we're getting there, right? And anyway, that's all. Thank you very much.
Oh, thank you. Let's thank you. Very interesting one. Thank you very much. We'll take some questions. There are a lot of questions. Are there questions? Yeah.
Like in this kind of solutions, when you really go in implementation, what I found that
Sorry, I can't hear you.
so what I'm finding that you are developing solution, even though you want an open solution or open platform,
That's right.
but we end up in the developing a solution for individual industry.
That's right.
No, actually, this is really the objective of the hub. Because before the hub, we have done about 35 projects with different companies, right? And for a period from 2016 to 2023, we have done about 30 projects. So all of these projects develop point solutions. So the hub actually is not doing that. Is combining, it doesn't look at the platform, is combining the technology. So the solutions are applicable to different sectors and different plants, right?
But you still don't have, I think the question is we don't have one unique model, it's for each sector, but we are working with the...
So what is like, what we have leveraged from different projects, what came as a common piece that you are reusing again and again?
No, it's not correct. The AI has been trained differently. So what is different in its application, right? It's its application of this. The difference is the training of the AI model. The model itself could be a used model, and typically is. Okay, so you have to train the model, and you have to produce the description.
Right. But for example, digital tool, let's not talk about the model, the
Yeah.
digital tool, for
Yeah,
example.
for the description is reusable. Okay? So you do it once for its production line. Okay, for the digital tools in its production line. Again, the model itself is also usable for the duration the production line stays the same and produce the same product or the same products. Okay? Now, if this changes, you have to retrain the model rather than develop new one. So the infrastructure that supports this is the platform for digital manufacturing is the same. And actually, we're now measuring actual productivity based on creating cost models with the productivity gains. So I hope I'm answering it.
Yeah, it's a difficult question. But like from a digital twin, can we use this all from research hub? Use it for have something
Well,
generic?
I'll tell you let's talk about it. I'll tell you what's reusable from the digital twin technology.
Yes.
Okay. First of all, it's reusable the tool you create to create the concept graphs.
Right.
All the protocols, industrial protocols, are existing.
Yeah.
They exist in IT platforms, plus an open source software. You can get MQTT open source and put it in there. So all of this, I think this is a lot more than you see in commercial IT platforms that provide a bunch of protocols, right? They don't provide anything else. It's a lot more usable than what you see in IT, in the IT infrastructure, right? And IT platforms provide value name pairs that don't provide concept graphs. Okay, and so that's and also we have the foundation of the concept graphs that is based on the standards, which are it's a standard way of describing this, and so on. So that's all reusable, right? And with AI, I mean, I will tell you the last thing I'm going to say. Go look at NVIDIA's physical AI. Okay? Go look at the industrial AI from Microsoft, which are platforms. They're all platforms, but they're quite generic platforms, quite limited. For example, the physical AI platform from NVIDIA is a special simulator for creating training data for AI models. Okay? Because the idea is, if you want to let's say you have AGV, you want to create, optimize the way it moves in the factory, you have to create data to train that one. So that's what NVIDIA provides. Okay? And that's the platform. That's all it does. And with Microsoft, it's variations of the existing products they have. Okay? They don't address even the training problem.
It's complicated. We need another research hub. I think we have to have. I think the research hub is 5 million from the government, and 7 million from the industry, 12 million, whatever. But I think the challenges are much more complicated than we thought.
Exactly.
Are very much more complicated. We are working also, we didn't mention, with Alamite, we are working with MEMCO in the aircraft. We are building some hardware and so on to monitor aircraft, just to get the compliance without looking at the digital twin and so on.
Yeah.
It's a complicated, but I agree with you.
I think that's the so the part of creating a better product, a good product. This is measured through an ISO standard.
Yeah.
So so when you create computer vision to assess the welding or to assess the CNC machine tools or the quality of the drills inside it, okay, the assessment method has to fit specific variables that they are provided by the standard they're using for inspection, for quality inspection. These are additional data. This we have to consider that when we build the AI, right? And it's part of the physical world.
Thank you. But just, I know where I'm at. No, you haven't finished. I have another question. I mean, we have been working together for a long time. What I want you is, what's really interesting on this project